Okay, so question number 3 is a system of two masses we see up here in the right corner. 30 degrees and 2 kilograms on the incline. So if we were to draw this, we have 30 degrees. We have 2 kilograms. Let's just put 2 here. And we have, oh, I can't bear 2 kilograms. All right. We have a pulley with string, some tension, and 1 kilogram below. That was awful. Here we go. Now there's a number of ways to do this. We can recognize there's a tension here. And there's a force of gravity. Let's call this force 1 gravity, because there's also a force 2 gravity here. And there's a normal force on this guy. And there's a force of friction. And I recall that the coefficient of friction, the coefficient of friction is kinetic friction is 0.6. So there's a number of ways to solve this, and one is through solving the simultaneous equations of the vector sum of the forces on each mass is equal to mass 1 times acceleration 1, and do the same for mass 2, and recognize that these two tensions are equal and opposite, that is, and the accelerations are the same, although in somewhat different directions. The way I'm going to solve it is different. I'm going to solve it as a system of masses and just say the sum of the forces on the system equal the mass of the system times the acceleration of the system. And so I'm going to pick a positive direction for the system, and that's going to be in this direction. Okay? Pulling down in that direction. And so we look at all the forces in those directions, and we're going to have the force of gravity on 1, okay, plus what are the forces on the system? Okay, we're going to take this force of gravity and we're going to break it into its parallel component, right? We'll call that force parallel, force 2 parallel, and then we have a force perpendicular, force 2 perpendicular. Okay, we recognize that this component of gravity is pulling into the surface and does not accelerate the system. Only this parallel component does. So I'm going to call that force 2 parallel. Okay? And then there's another force, and that's a force of friction here, plus the force of friction is equal to the mass of the system, which is mass 1 plus mass 2, times the acceleration of the system. Now I haven't addressed sign properly. Okay, this is pulling in the positive direction, right? Force 2 gravity is also pulling in the positive direction, so that parallel component is pushing us along. But this is in the negative direction. Okay, so we can write these down now. This is 1 kg. Maybe I can just jump in to make this a little bit easier. This is 1 kg times the acceleration of gravity. M1g is equal to 10 newtons. Okay, this is 20 newtons. So it's 20 newtons. Okay, the parallel component, that sine 30 is 1/2. So this is 1/2 of that. So we recognize then this is 10 newtons. Okay, it's 1/2 of the full 20 newtons. And this is 10 newtons. Okay, now we need to find the force of friction. How are we going to find the force of friction? I know. Force of friction is equal to mu times the normal force. So what's the normal force? We look at the acceleration in the perpendicular direction, and we realize it's not accelerating at all in this direction. So the normal force must be equal and opposite to the perpendicular component of gravity. So that must be equal to 20 newtons times the cosine of 30. All right, and the cosine of 30 is 0.87 approximately, and mu is 0.6. Right? So 0.87 times 2, that's what? That's 17. Is that correct? Times 20 is 17. So the normal force is equal to 17 newtons. Right? Times 0.6 is 42. Okay, that's 10.2 newtons. And so what do we have? 10.2 newtons is equal to that 3 kg times the acceleration of the system. But remember, this is a frictional force, and so these more or less cancel, and I have a total of 10 newtons is equal to 3 kg times the acceleration of the system. So the acceleration of the system is equal to about 3.3 meters per second squared. Okay, it's a little bit less than that because this is actually a little bit greater than 10. This is 9.8 newtons. So, maybe it's really closer to 3.2 meters per second squared. But this is a good ballpark figure. Whoops. Now I got myself into trouble. Okay, so what's the tension? Now the first thing we think, erroneously, we don't want to do this, is 10 newtons pulling down, 10 newtons pulling up. But if that were the case, this would be an equilibrium, and it's not. The acceleration is downward at 3.2 meters per second squared. So what does that mean? The vector sum of the forces must equal mass times acceleration, which for this guy, 3.2 meters per second squared, 1 kilogram, is equal to 3.2 newtons. So the total force pulling down on it must be 3.2 newtons. Gravity gives you 10. So the tension must be 6.8 newtons upwards. So you got 6.8 newtons pulling up, tension, 10 newtons pulling down. The resultant force is 3.2 newtons, accelerating it at 3.2 meters per second squared. Hope that was helpful.